So now that we have a hand with angles, we're going to talk about trig functions, because really these just correspond to particular angles. So one thing you have to remember is our Pythagorean theorem. It comes into big play here, but specifically in a right triangle. When you take a squared plus b squared, it equals c squared. A and B are the sides that form that 90-degree angle. They're the legs of our right triangle. And then C is that hypotenuse. What we're going to take a look at are similar triangles. So similar triangles are triangles with equal angle measure, okay? So they have varying side lengths, but they're scaled up or scaled down versions of one another. Specifically, we're going to focus on similar right triangles. So maybe I have my first right triangle that looks like this. It's got that 90-degree angle here. And then basically to get my other triangle, I'm going to scale it up. So I just go ahead and stretch it out to form a bigger triangle. Let's go ahead and make it the same shape or same size. So the angles are unaffected at all. I've just multiplied side lengths by something. So if I call this side A, then this one would maybe be side capital A. Or let's even use different letters. Let's call this X. If this is side B, then side Y is the one that corresponds to it. And then side C is going to be our hypotenuse. Let's make that side Z in this second triangle. The 90-degree angles are in exactly the same spot. Again, stuff can be rotated around, but these two angles are exactly the same. And then this angle here, which if I call it theta, would be exactly the same as the one here. And then that forces that third angle to also be the same because these two angles are complementary, okay? So because you know similar triangles are proportional, I'm just taking side A, maybe doubling it to get to side X, maybe timesing it by 1.5. We know that sides of similar triangles are proportional. This divided by this would be the same as side B divided by side Y. So if I take the two corresponding sides A and divide it by X, it's exactly the same as if I take side B and divide it by Y. Okay. So A and B are from the same triangle, X and Y are from the same triangle, A and X are the same side on that different triangle, and same thing, B and Y correspond to the same side. So really, I can flip-flop these a ton of different ways, and I know they're going to be equivalent. So what we can do is we can go ahead and cross multiply to get A times Y is equal to B times X. And then I'm going to go ahead and I'm going to bring the B to the other side. So that would be by division. But then I'm going to do the same thing. I'm going to bring Y to the other side. So really rearranging it one more time gives me A over B is exactly the same thing as X over Y. Okay. A and B now come from the same triangle. And when I scale up that triangle, the ratio X over Y is exactly the same thing. So really, you can do this a ton of different ways, but the ratio A divided by B will be exactly the same thing as X divided by Y. Likewise, I could arrange this a different way. B over A would be the same thing as X over Y. And then I could pick sides B and C and Z and Y and get the exact same thing. So these angles are really the only unique thing that identify the triangle. The ratio of the triangles are always going to be similar for these, okay? So in total, you're really going to have 6 different ratios. This is the first one, but again, I could have flipped these and I could have done B over A by dividing by A and then bringing X to the other side. So that gives you your second ratio. Pairing B and C and Z and Y together gives you 2 more ratios because again, the flip. And then also pairing A and C and Z and X together gives you 2 more triangles or 2 more ratios. So ultimately you have 6 different ratios, and these are referred to as our trigonometric ratios. Again, the triangle is really only defined by one angle because the other is a right angle. So if I know that angle, I immediately know all of these different ratios, what they have to be. So in total, there are 6 possible ratios of sides. Each one of these has a name, and those are our 6 trig functions. So I'm going to look at a triangle. We've got main trig functions, and then we've got reciprocals. We have sides x and y, because really what happens is we're going to put these on an xy axis. So x is going to be this part, y is going to be this part. R is our hypotenuse. And this one angle defines the entire triangle. So x is considered to be the side that is adjacent to that angle theta, because it is connected to theta. Y is the side that is opposite the angle. So we call this one the opposite. And then R is the hypotenuse of our triangle. So our first trig function is sine of this angle. So the way we denote that is by just sin, sine of this angle theta. This is going to give us one of our specific ratios, and this is going to be y divided by r. So the way you can think of sine is it's the opposite side over the hypotenuse for that angle. So opposite over hypotenuse. Cosine is denoted by cos of, again, that angle theta, because that defines this triangle. This specific ratio is going to be x divided by r. So cosine you can think of as the adjacent divided by the hypotenuse. And then tangent is our last main trig function. This is going to be found by taking y and dividing it by x. So tangent we denote with just tan, and again it's of a specific angle theta that defines this triangle. So it is y over x. So the way you can think of tangent is it is the opposite over the adjacent. Okay? If you can remember these 3 ones, they're called our main ones for a reason, because the other 6 just come from flipping everything. So we do have a phrase to help us remember each of these pieces. You're going to hear me use SOHCAHTOA a lot. So the way I like to write this, so, S-O-H, sine is opposite over hypotenuse. Ca is C-A-H. Cosine is adjacent over hypotenuse. And TOA. So tangent is opposite over adjacent. Apologize for my dog barking in the background. So these are our 3 main trig functions. The reciprocals, if you notice, kind of are very similar to each other. So you have cotangent, that's going to relate to tangent. Then you have secant, cosecant, kind of goes along with cosine and sine. You'll see that word co in here a lot. But the reciprocal of sine is going to be a function cosecant. So we denote this with CSC of an angle. This again is just the flip of sine. So instead of y over r, it's r over y. Secant is going to correspond to cosine. So this is denoted with SEC of theta. It is the flip of cosine. So this is r over x. And cotangent is denoted with COT, which is the reciprocal of tangent of theta. So this is x over y instead. Okay. So you have to be really careful. These trig functions all need an angle on the inside. You can't just write tan, it needs an angle in there. Because again, that angle immediately tells you what those fixed ratios are. So I can never ever just write tan is equal to 2/1 or something like that. It needs an angle, okay? And then with this, we also do have some connections because it is a right triangle. So if you take x squared plus y squared, it better equal the hypotenuse squared. And then if you really don't have side r, go ahead and just take a square root. We do not need to worry about the plus or minus because we're going to be working with triangles. The quadrant is going to tell you whether it's positive or negative. We like to consider the hypotenuse to always be positive. The other thing that ends up happening, if you notice, we also write this in a very particular order, because if I take y and divide it by x, that's my tangent. So if I take sine, which is y over r, and divide it by x over r, those over r's cancel each other out. So really what ends up happening is that tangent of theta can be rewritten as sine of theta over cosine of theta. And that means cotangent of theta is the reciprocal, so it is cosine over sine. Okay. So let's try an example, just getting some practice with this so we can find all of these 6 different trig functions. We're told the terminal side of an angle, theta, passes through the point 8, -4. We want to calculate the values of the 6 trig functions. So I'm going to go ahead and I'm going to start by drawing a picture. So we've got our xy plane. My point is 8, -4, which would be somewhere over here. I don't have to be super precise with it. But what this does is it ends up forming a right triangle. So there is my point 8/4, and here is my right triangle that I can go ahead and draw in. Okay, so in this case, my x value is -8. So the side of this triangle we consider to be -8. Y would be the vertical distance. And then I need to figure out what this value of r is, okay? So ultimately, I'm concerned with this angle right here to figure out what all the different pieces are. But our actual theta value is right here, okay? But I'm going to use this right triangle to be able to figure out, because it's just all my trig ratios are based on x, y, and r values. So to figure out what r is, we just use the Pythagorean theorem. So that gives us r is x squared plus y squared. So r is the square root of 64 plus 16, which gives us the square root of 80. And I definitely need to simplify this. So if you divide it by perfect squares, 80 is the same thing as 16 times 5. So my hypotenuse of the triangle is 4√5. Okay. So now when I want to find tangent of theta, I'm just using this right triangle. And again, it's because you can't really draw a right triangle with an angle theta, but this still defines one right triangle in our xy plane, okay? So let's figure out what each of these trig functions is. So sine of theta, remember our phrase, I'll write it over here so we have it. It's so katoa. Sine is opposite over hypotenuse. So opposite would be 4, hypotenuse is 4√5. So it's the y value over r. So 4 over 4 root 5. So we want to go ahead and simplify this. At least, thankfully, the 4's cancel. And that gives me 1 over root 5. And then we really don't like radicals in the bottom, so you do need to rationalize these. So you times it by root 5 over root 5. And so rationalized sine of this angle would be root 5 over 5. Which then immediately tells me what cosecant is, because it is the flip of sine. You do not need to use this version. Go ahead and use the unrationalized. If you flip that, it's root 5 over 1, so cosecant of this angle will be root 5. To find cosine of the angle, that is adjacent over hypotenuse, so that is x over r. My x value is -8, and again, my r value is the same. It is 4 root 5. So if I go to simplify this, 4 over 4 into 8 gives me 2. This is -2 over root 5. But I again need to rationalize it, so we times it by root 5 over root 5. And our rationalized version is -2 root 5 over 5. So this also tells me immediately what secant of theta is. We flip cosine of theta. And again, don't want to use this version because that would put the radical back in the denominator, and I don't want that. Use the unrationalized. So that gives us root 5 over -2. So really just overall, it's negative. Last but not least, we've got tangent of theta, which is opposite over adjacent. The opposite side is y, adjacent is x. My y value for this point is 4, my x value is -8, and that simplifies nicely to -1/2. Cotangent of this angle is the flip. So really it's -2 over 1, which overall is just -2, okay? So really when you have sine of an angle, because again, that angle can end up anywhere in quadrant 3, you're really always going to use a triangle that helps you out just based on that position. So if my triangle or my terminal side ended up here, I would use a triangle looking like this to be able to figure out what all my pieces are. So what ends up happening if I look at these trig functions in each of my quadrants, that's ultimately going to tell me what sines they're going to be. So as long as you know sine, cosine, tangent, you can immediately get all these reciprocal functions, which again is why we put our main focus into these 3 trig functions. So we've got our xy plane, we've got our 4 quadrants. If you think about in quadrant 1, here both your x and y values are positive. And your r value is always considered to be positive as well. So x, y, and r are always positive in quadrant 1. That means all of your trig functions are going to be positive. When you move into quadrant 2, your x value is negative here, but your y value is positive. So cosine is the one that deals with x. Cosine would be negative. Sine deals with y, so sine is positive. Tangent deals with dividing these two, so since one is positive, one is negative, it's overall negative. So really what happens in quadrant 2, sine of theta is the only value that's going to be positive, which in turn makes cosecant positive, okay? Which is exactly what we had up here because we were in quadrant 2. So you see sine is positive, cosine's negative, tangent is negative, which then tells you the reciprocals. If your terminal side lands in quadrant 3, well, here both x and y are negative. So that means sine and cosine are negative. But when you divide two negative numbers, it turns positive. So in this quadrant, tangent of theta is the only one that is positive. Finally, in quadrant 4, x is positive, but y is negative. So cosine's positive, sine is not. And then when I divide these two, them being different signs means it's overall negative. So only cosine of theta will be positive here. Okay. So there's a little phrase to help you remember what the signs of each trig function are in each quadrant. It's all students take calculus. You can come up with a different one if you want to help it make sense, but this is our most common one. So all are positive in quadrant 1. Sine is positive in quadrant 2. Tangent in quadrant 3, and cosine in quadrant 4. So all students take calculus. Okay? So let's try another example. If cosine of theta is 24 over 25, and the terminal side of theta lies in quadrant 4, we're going to find sine of theta and tangent of theta from that. Okay? So again, I'm going to draw a little picture to help us out. We have our xy plane. The terminal side of our angle lands somewhere here in quadrant 4. So the angle theta is really the whole one over here, but that really, again, defines one particular angle here. So we use that to figure out the opposite adjacent. So I'm going to go ahead and I'm going to draw a right triangle in, if this will let me. Close enough to a right angle. Okay. So this point, or our cosine of theta, is 24 over 25. I don't know the actual point yet. But cosine is going to be the adjacent over the hypotenuse. So this side would be the adjacent, so we can say that's 24. And the hypotenuse is r, that's 25. We need to figure out what y is to be able to find sine and cosine. But I at least know, because I'm in quadrant 4, that my y value is less than 0. Okay. So to actually find our y value, we just use the Pythagorean theorem. X squared plus y squared needs to equal the hypotenuse squared. X squared is 24. We don't know y. And then r is 25, which I accidentally miscopied right here. Sorry about that. Okay. So if you take 24 and square it, that would give you 576. 25 squared will give you 625. So solving for y squared, we subtract 576. That gives us 49. And then here is where we take a square root. So square root of 49 is 7. And again, technically you get plus or minus. But in our case, because we're in quadrant 4, I immediately know it's the negative version. So my y value is going to be -7. Okay. So now that I have my full triangle, that tells me sine of theta is going to be opposite over hypotenuse. My y value is -7. My hypotenuse is 25. And then tangent of theta is going to be opposite over adjacent, TOA. So opposite is y, adjacent is x. So this gives us -7 over 25. 24. All right, so we're soon going to get to the ranges of each of these different trig functions, but I'm going to start by talking first about quadrantal angles. So we know 90 degrees, 180, 270, that lands us on the quadrants. But what are the trig functions for each of those values? So really it just comes down to using that same idea. It's going to be x, y, r, all of those trig ratios. So starting out, x is the same thing as, or starting on the positive x-axis is 0 degrees. Up here is 90 degrees. Here is 180, here is 270, and then you land back at 360 going all the way around. So in the same way that if you scale up a triangle, the ratios are the same, does the same thing here. So you can really pick any point on each of these axes. Easiest points though are just a distance of 1. So this point here would be positive 1, 0. This point would be 0, 1. Here is negative 1, 0, and then 0, negative 1. So if I start out right here, which is 0 degrees or 360, your x coordinate is positive 1, your y coordinate is nothing, and then r is the square root of x squared plus y squared. You don't have a triangle, but it's really just the distance out to this. So your value of r ends up being 1. So if I look at sine of 0 degrees, that's going to be y over r. Sine of 0 is 0. Cosine of 0 degrees is going to be x over r. So that gives me 1 over 1, which is 1. And then tangent of 0 degrees is really the flip of these. It's going to be y over x, so 0 over 1. Tangent of 0 is 0. Okay. Moving on to 90 degrees, here your x is 0, your y is 1, which again gives you 0 squared plus 1 squared is r squared. So your r is also 1. So when we look at sine of 90 degrees, that's y over r. So we get 1 over 1, which is 1. Cosine of 90 degrees is x over r. So that's 0 over 1 or 0. And then when we try to find tangent of 90 degrees, it's y over x. So you do run into a problem here. Tangent of 90 degrees is undefined. Going on to 180, it's really very similar to 0 degrees. The only difference is your x is negative. So my x is negative 1, my y is 0, but again, r is going to be positive. So negative 1 squared plus 0 squared gives you 1. Square root it gives you 1. So sine of 180 degrees is y over r, which is 0 over 1 or 0. So same thing as 0 degrees. Cosine of 180 degrees is going to be negative 1 over 1. So you get negative 1. And then tangent of 180 degrees is going to be 0 over negative 1 or 0. Last but not least, our fourth quadrantal angle is 270. So here your x is 0, your y is negative 1, and again it leads to the radius or r, the hypotenuse, being positive 1. So sine of 270 degrees is going to be negative 1 over 1, giving you negative 1. Cosine of 270 degrees is going to be 0 over 1, or 0. And then tangent of 270 degrees is going to be -1 over 0. So again, we run into an issue here. This is undefined. So hopefully you kind of notice something nice actually happens when you look at 0 degrees. You get the point 1, 0. That's what it goes through. It's exactly the value of those trig functions at 0 degrees. When you look at sine and cosine of 90, sine of 90 is 1, cosine of 90 is 0. Cosine of 180 is -1, cosine or sine of 180 is 0. And then same thing down here. Cosine of 270 degrees is 0. Sine of 270 degrees is -1. So these points are actually really important for us because we are going to go through something which is our unit circle. And really the points on that circle tell you exactly what sine and cosine of those angles are. So now that we have a little bit of a hang on these quadrantal angles, we're going to talk about the ranges of all of these different trig functions. So again, that angle theta can be anything between 0, 360, and really it can go even further after that because we know we'll just land back in the same terminal side and we can find a different angle corresponding to it. But we'll get to all of that very soon. But the idea is I'm going to just fix my radius to be r because then what I can do is if here is r, for this x and y value, I have one triangle. If I pick this xy value over here, again, I have a right triangle with a different angle, but the same hypotenuse. So we're fixing the hypotenuse. And this allows us to then create a triangle with an angle between 0 and 360 degrees. So ultimately, that triangle then is going to trace out a circle where your x and y are going to vary as your theta goes between 0 and 360 degrees. And so your value of r here will then create a right triangle, and it has some point xy to give you those sides x and y. And then our theta is formed, okay? So as I fix the hypotenuse r and I trace this around, letting x and y vary, theta is going to increase and we get that circle, and still the same ratios hold. Sine of theta is found by taking y over r, and cosine of theta is found by taking x over r. So as theta increases from 0 to 360 degrees, all of your points x and y are going to be on the circle. This value here would be whatever we fixed r to be. This value is r, this value is -r, this value is -r. Your x and y values are never going to go past those values. So I'm not picking a point over here to create a triangle, I'm just picking one on the circle. So really, once I fix the hypotenuse r, my x and y are trapped between -r and +r. So really, if I manipulate these, if I divide everything through by r, that would be -1 is less than or equal to y over r, which is less than or equal to +1. Well, y over r is exactly sine of the angle. So I end up with our sine function is trapped between -1 and 1, no matter the angle I plug in. And likewise, we can do the same thing for x. If we divide through by r, that gives me -1, x over r, and +1. And that's exactly cosine of our angle. So our cosine function is also trapped between -1 and +1. So it will not make sense for cosine of our angle to equal 3, okay? But the other way you can look at this, if you have a right triangle, your leg cannot be bigger than the hypotenuse. So x over r is always going to be less than 1 or equal in the case of the quadrant angles. It can be -1 because you have your x being negative values. And same thing here, y is a leg of the triangle. It cannot be more than the hypotenuse, okay? But now when it comes to our other trig functions, it's a little more complicated. Since x and y can really be anything on this circle, there's no telling how small or big their ratio is. Because again, if you think about those quadrant angles, for some values it's 0, for some values it's undefined. Because if I pick a point like right here, my x value is so small, but my y value could be like 5. Doesn't matter though, because 5 divided by a small number blows up to something huge. So really your tangent and your cotangent function can be anything you want. The range is -infinity to +infinity. So for the sine and cosine function, the ranges are going to be -1 and 1. That is the only outputs you're going to get, okay? Since tangent of theta, however, is y over x, and cotangent of theta is x over y, and x and y can be as big or small as they want, both tangent of theta and cotangent of theta can take on any value. So i.e. their ranges are both -infinity to +infinity. Tangent of theta can equal anything. Your secant and cosecant are a little bit weird, but they match up together just like sine and cosine do. But since cosecant of theta is really the flip of sine, and sine is something between 1 and -1, well, you take 1 and divide it by a decimal in between 1 and -1, you can potentially get something big, or you can get something big and negative. So since secant, cosecant is 1 over sine, and secant is 1 over cosine, the smallest you're ever going to get is 1. So if sine is 1, then cosecant is 1. If cosine is 1, secant is 1. Okay? But if cosine is 0.5, 1 over 0.5 gives you 2. You'll get something bigger. If cosine is super close to 0, 1 divided by a very small number is huge. And likewise, the same thing for the cosecant function. If you have a negative number, sine could be -0.5. 1 divided by -0.5 is -2. And then if it's sine is like -0.00001, 1 divided by that is a ridiculously large number. So essentially you're going to get the opposite of this. So it's going to form the entire real number line. So what we get is that cosecant of theta is going to be at least 1, or it's going to be at most -1. And same thing, secant of theta is at least 1, or it's at most -1. So essentially their ranges can be defined by two intervals. It can be something from negative infinity up to -1, including -1, or +1 to infinity. You won't get anything that's in that sine and cosine range, okay? So we'll try an example. We're gonna see, is the statement possible or not? And we're gonna start with secant of theta equaling √3/2. So if you plug that into your calculator, √3/2, you should see is 0.866 roughly. And that does not fall inside this interval. So this is not in negative infinity to -1 or 1 to infinity. So this is not possible. If I say sine of theta is equal to 0.08, well, I have no problem here because 0.08 is in the range, which is -1 to 1. So this one is good. Okay. So it's going to take some time to get used to these different trig functions and all of the components of it. Again, we are going to work with these 6 basic trig functions through and through throughout the semester. So take your time with this homework. Make sure you understand that these are just sides of a triangle in whatever quadrant, okay? So we're going to go back to those signs of these. We're going to find the signs of the 6 trig functions for this given angle. And then we're going to see if we can identify the quadrant where for the angles satisfying whatever conditions they tell us. So starting out with this one, we're given an angle of -233 degrees, and we want to figure out what sign is each trig function. It's real annoying. I know we have sine, S-I-N-E, and then S-I-G-N. You can say sin if you need to, but it's unfortunate that that's just the terminology we have. So that angle being negative tells us we're going to move in the clockwise direction. I'm not so good at writing and speaking simultaneously. But this starts out with 0 degrees, and now I want to go negative, so I'm going to go backwards. So down here would be -90. Here is -180, and here is -270. So if I think about -223, that's somewhere in between -180 and -270. So I don't know exactly, but somewhere around here, this is where the terminal side of my angle ends. And so here is our angle theta, which is -223 degrees. Okay. So I'm in quadrant 2 for the terminal side of this. So in this case, your x is negative and your y is positive. Okay. You can really just use your phrase, all students take calculus to figure out which ones are positive. But if you think about sine of theta, that's going to be y over r. So if I'm in quadrant 2, it is positive, which immediately tells me that cosecant of this angle is also positive because I just flip it. Cosine of theta is x over r. In quadrant 2, x is negative. So this tells us cosine is negative, which in turn means secant is negative. Because again, I'm in quadrant 2, sine is the only thing that's positive. So cosecant is the only reciprocal that's positive. So when you get to tangent, I already know this is negative, but it's y over x. Y is positive, x is negative, so this is negative, which tells you that cotangent is also negative. Okay. So being fluent in these properties is really helpful. You are going to draw pictures a lot. You're going to draw the XY plane very frequently. Okay. Let's try one more. we're going to identify the quadrant for the angles satisfying the given conditions. So again, I'm going to start out just by drawing this. We've got quadrant 1, 2, 3, 4. All students take calculus. So all trig functions are positive in quadrant 1, just the sine function in quadrant 2, just the tangent function in quadrant 3, and just the cosine function in quadrant 4, which again tells you about the flip. Cosecant of an angle is positive here, cotangent of an angle, and then also secant of an angle is positive. So if I know sine of alpha is positive, well, that's going to happen in quadrant 1 because they all are, and in quadrant 2. So the only angles that make this true are the angles in 1 and 2. If I'm looking at secant of theta being positive, that's exactly the same thing as saying cosine is positive. Well, that's going to happen in quadrant 1 and quadrant 3. So if I want both of these to be true, I'm looking at the overlap, and that is only quadrant 1. So the only way this can be satisfied is if our angle lies in quadrant 1. If I switch my conditions and I look at where tangent of beta is less than 0, so I need tangent to be negative, here's where tangent's positive. So where it's negative would be quadrant 2 and 4. If cosecant is negative, that's the same thing as saying sine is negative. So here's where sine's positive, so this happens in quadrant 2, or quadrant 3 and 4. So my angles that satisfy these two constraints are only the ones that are in quadrant 4. So again, these 6 trig functions just come from ratios of triangles, but that triangle we can put in the xy plane to give it positive sides, to give it negative sides, but the hypotenuse we're always considering to be positive. So we can find sine of a ton of different angles. We're going to talk a lot about special angles because of special right triangles that we have, and those you're going to have to eventually become very, very fluent in. So take your time with these, but these first couple sections are fundamental, just working with angles and understanding what these 6 different trig functions are.